I'd like to introduce Rhys Goldstein from Autodesk, who is going to be talking about the kind of the infrastructures that you might use for modeling. Yeah, go ahead. Thank you, Rhys.
Yeah, great. Thanks a lot, Greg. So this is an effort that we've been engaged in for almost 10 years now. And it really started off with this goal of changing the way simulation is developed. So one thing we want to do is shift away from modeling a single phenomenon with a single paradigm at a single scale to modeling complex systems that may involve many different phenomena interacting with each other. Uh, and also we want to help people shift from working more independently as we saw it. There were communities of researchers where every lab basically had its own simulator, and uh, all the simulations were separate projects, to a more collaborative approach where the entire community is really working together towards advancing their collective uh, simulation capabilities. So that's what we mean by making simulation code scale. And we've come out with this framework called SyDEVS, which is open source and free to available to use. So I'll be introducing that. But more importantly, I'll be introducing the sort of the vision for what scalable simulation development looks like. All right, so let's begin. And the first thing we're going to do is we're going to really clarify what this change would look like. So let's start with a simple question. How do we write simulation code? And the most basic answer is that it looks like this. So you initialize a bunch of state variables. Uh, then you have a time variable, and you set it to 0. You have a loop while time is less than some end time. Then you update the state variables, and then you advance time. Time equals time plus a time step. So it's a very simple type of program. It works for many simulations, and there's nothing complicated about writing a simulation in general. But of course, if you just took this template and tried to expand it, eventually it would get very complex, and probably wouldn't scale beyond a certain point. So how do we move from this to writing complex system simulation codes where you have many phenomena? You want to use different paradigms, maybe data-driven modeling, physics solving, agent-based modeling. You want to put them all together and at different scales. So how do you work towards this? So I think the obvious answer would be, oh, why don't we just use object-oriented programming? So you might come up with something that looks like this. Like you've got something you're trying to model, a traffic intersection. You define a class and then define the variables and methods for that class. The idea being that if you then do another class for buildings and roads and vehicles, you'll eventually be able to model a complex system. But even this we find doesn't really scale. And the reason is even when you're taking this modular approach with object-oriented programming, you still have dependencies, and the dependencies go all the way through your classes. So in here we've got a traffic intersection, but it depends on a traffic light, a road model, a vehicle model, a weather model, and over time you build up more and more dependencies between classes, and it's very hard to change anything. If you change one thing, it might affect all these other classes. So as the simulation becomes more complex, people are less willing to change it. Eventually they'll say, okay, we can't change anything now. We just have to keep using it as it is, because anything we change might break something. And then that goes on for a little while. And then sooner or later, the decision is made to rewrite the whole thing from scratch. And then the cycle repeats. So what we want to do is get away from that cycle and have a continuously evolving and improving uh, sort of collection of models. So how do we write complex systems code that scales? Scale meaning that as you bring more people into it and continuously improve things and add new models, you can keep going and do what you want to do without having to throw it out and start over again. Okay, so this is what that looks like, and the approach that I'm gonna present is probably the more ideal approach. There's other approaches, but the ideal is this. So what you do is you choose a common form for all simulation models. So this is the image is showing you a common form, which we'll go through in more detail. And the idea is that all models can fit in this form. I'm sorry. Okay. Sorry, forgive the little phone call. All right, so now this may seem like a radical approach. I hope it is. It does seem a little bit radical because it's not how we do things. But let's see what this would look like. So the idea is you have a bunch of people contributing models in a common form to a central repository, and then that repository grows and grows, and then you create systems models by connecting a subset of all these models together. So then here you've got a bunch of models in the repository being connected that would form one system simulation. And because they're all in a common form, it's possible to connect them all. And you can form another system simulation by connecting a different set of models. I know this, of course, supports reuse because you can have some of these nodes that are common to multiple systems. And more importantly, you could replace them. So if you don't want one of the nodes and you want to replace it with another one, you could just do that by severing connection and adding a new one. This is actually very difficult to do if you have a lot of dependencies, because then it's very hard to just remove something. Remember, a scalable system is not defined by how much you can just add to it. A system becomes scalable if you can remove things from it. If you can remove some functionality from a system without really having to change the whole system, then that's a indication that the system is scalable. Okay, so this is what the approach looks like. Now let me give you some examples. Oh, sorry, before we do that, I just want to mention one thing, and that's this isn't an entirely new approach. Modelica is based on the same approach, where you've got the Modelica simulator and people contribute Modelica models to a repository, and then they can be linked together. So this approach does support scalable simulation in practice. But why don't we just use Modelica then? Well, and there's nothing wrong with Modelica, by the way, but this is the thing. Modelica uses a certain type of simulation method. It's an equation-based paradigm. Whereas what we want to do is support just basic procedural code. So we all know how to write procedural code. It's the standard way of writing simulations. We want to stick to that procedural paradigm, but still be able to benefit from this approach where all the models are in the same form. Okay, now let me show an example. So this is the area that I tend to focus on, which is human building interaction. So you might have a complex system for a building that involves weather, thermodynamics, heat, like a heat source, acoustics, human behavior, and you want to combine them all together. And here's some work we did at Rutgers with SyDEVS, and it's a simulation where you can see people coming into a building and moving through the building using their Steer Suite simulator, which we then hooked into SyDEVS. And then you can also see the red, which is the temperature, which is increasing in response to people's body heat. We're also looking at sound simulation. So here's the sound of people walking. And so the point of this type of simulation is to give designers more insight into how they might design the building to, say, minimize distraction, to sort of improve people's experience in the building, perhaps to design an HVAC system. And for these types of insights, it's important to model the different aspects of a building as they interact with each other. And here's one last example where we're showing an animation of people moving through a hotel. The yellow lines are people going through. You've also got temperature in red there. The heat is diffusing into the building. You've got windows being opened by the occupants in response to the temperatures. Then it cools down inside. So a whole bunch of different phenomena all interacting. Okay, so that's the vision. But now let's talk about this common form that makes it all work. A common form for all simulation models. And here's what it looks like. It consists of 4 nodes, but the main one is this atomic node. And so that's what we're going to focus on the most here. So here's the atomic node. So at first, we have a set of flow input ports, but you can think of them as parameters. So these get supplied to the simulation before it begins. Then you invoke the initialization event handler, and that initializes the state variables of the model. The model has to be able to receive inputs during a simulation. So you've got message input ports, and whenever you receive an input, message input, it triggers an unplanned event. So you have a handler for unplanned events. A handler, by the way, is just a function, really. Now, the unplanned event also takes as input a time value called the elapsed duration, and that's very important. And it's one of the things you don't really have if you just use a standard object-oriented approach. So you need that elapsed duration that tells you how much time elapsed since the previous event. And you also
Wait, question.
Yeah.
So do you have a global time, or does each object have its own local time?
Yeah, I guess that's a great question. So the global time is handled completely separately by the simulator. So there's a simulator that's completely separate from all the models, and that keeps track of the global time. Inside the each model, you only have this. I guess you could call it a local time, but I would think about it in terms of this elapsed duration and the planned duration that you're going to see. But you have these relative time values. Now, if you really want a global time, you can have a state variable called time, and you can set it to 0 at initialization, and then you can keep adding the elapsed durations onto it, and that will give you a global time. So you can do it if you want to. Does that answer the question?
Oh yeah, thank you.
Yeah. Okay. So now both of these event handlers have a planned duration that comes out of them. So they set this planned duration, and that determines when a planned event will occur. So if no message input is received in that time, you get a planned event. And then a planned event can produce message outputs, and it can produce these during a simulation. And it also produces a planned duration for the next planned event. So just think about a simple physics model. In a simple physics model, you just have a time step, and you keep updating your state variables at each time step. So in that case, you would just basically have planned events, and every planned duration would be the same value. But you could also imagine maybe a data-driven model where every time you get input, you want to do something in response to that input, maybe based on data. And so in that case, you need these unplanned events too. I apologize for the ringing in the background, but I'll move on. Finally, there's a finalization event handler, which also takes the elapsed duration, and then that, if needed, that can produce a set of flow outputs, which you could think about as statistics that describe what happened. In practice, though, you don't tend to really use the finalization event or the flow output ports very often. It's really the first three. So that's the basic form, and the claim is that it works for essentially any simulation model. It doesn't matter if it's physics based or data driven or what have you. You can fit it into this form. It's kind of like a state machine, but it includes time. Okay, so that's the basic idea. That's the atomic node. And this has been known, by the way, since 1976. That's when the theory came out. It's called DEVS. But if you look up DEVS, you'll get this description that you see here. And we really found it was a little difficult to approach. For one thing, it wasn't symmetric. So what we've done is we made it symmetric. Whereas if you look at our alternative formalism and then look at the diagram here, you'll see you've got the 4 ports, the flow input, message output, flow output, and they sort of correspond in pairs. You've got the 4 associated event handlers, and then you've got the elapsed duration that comes into 3 of the event handlers, and the planned duration that comes out of the other 3. So it's a very symmetrical formalism in the way that we've presented it, which is, I would claim, pretty much equivalent to the original definition, but just it's sort of rearranged. For example, we merged some functions together. Now, best practice would be to always define your models using formulas first. But to be honest, only a simulation theorist would really take the time to do that. Most people would just go straight to code, and that's fine. So this is what it would look like in code, and here we're using SyDEVS. So you're coding, here we're coding a particular model, and let's compare that to the diagram. So the model as a whole is defined on the top. In this case, we're calling it a worker node, and it inherits from atomic node. An atomic node comes from the SyDEVS library. You'll also get a composite node and a collection node, so you can inherit from those as well. So we've got flow input ports. Those are specified right there. In this case, there's 2 flow input ports. You've got your message input ports. In this case, there's 1. Message output ports. In this case, there's 1, and no flow output ports in this case. You've got your 4 event handlers, and those are the elapsed durations. They come in as arguments, and the planned durations get produced as return values. And let's just look at one of those functions. So we're going to look at the unplanned event. So here's the function, and it's just C++ code. So at the end of the day, it all comes down to the code that we're used to at the very bottom. But the point is that we structure this code in the form of these modules that have this common form, and that allows us to use one simulator to connect, all these different combinations of models. All right, so that's the atomic node. I'm gonna move on now to the composite node. I'm not going to cover these all in detail, but we're going to spend some time on the composite node. Before we get into that, though, I just want to let me just sort of switch over to some basic concepts here.
I'll ask you a question about kind of the flavor of modeling. So first, this seems like a deterministic system, or can you incorporate probabilistic models into it as well?
Yes, you could. They can be probabilistic or deterministic. So, yeah, I think the key thing to remember is that in the end, each of these event handlers, if we go back to the atomic node, each event handler is just a bunch of code. So if you want to generate a random variable and then choose choose your next state randomly, you're totally free to do that. You can choose your outputs randomly. If you want to have your node access a database and then maybe sample information from the database, you can do that. So that we definitely use this for stochastic models. We're very interested in modeling human behavior, which we often do stochastically.
Well, then let me ask you one variant. What about pushing probability distributions around as your state? I mean, I'm thinking like a Bayesian probabilistic.
Yeah, so you definitely can draw from probability distributions, and you want to pass those around. So you have to think about when do those distributions change? Like if the distribution is constant, you want to give the parameters of that distribution in the initialization event. But if you want the distribution to change over time, then you have to supply the new parameters or information to derive the parameters from through those input messages. So
right, we'd be patching the data on the message would have to be a distribution. Okay, that makes sense. And then presumably your solver would have to be a Bayesian kind of solver, not like a deterministic engine, right?
Yeah. So for example, here, this is an unplanned event. So this can take input. So if we look at the first line, it says if this variable, or if this value called break dn input is received. So here you could receive a parameter of a distribution, or you could receive just any value that allows you to derive or modify a distribution. And then in this code, you could change a distribution. And then in your planned event, that's where you might draw a sample from the distribution and output it. Just one example, of course. Yeah.
Then one more question, maybe not for now, but just at some point in time. Can you compare this to a system like Kepler that seems like a higher level thing that kind of says, here's like deterministic agents, the stochastic agents, they have more categories of kind of algorithms or just continuous discrete, they have it as high level abstractions. This appears to be more like a lower level abstraction than that.
Yeah. So the atomic node that I was presenting here is like the lowest level of all the nodes. So I mean, it might help. It might help if I go on a little bit and we come back to that. Yeah. Okay. All right. Let's go into the composite node. And before we dive into it again, I just wanted to highlight a few concepts of how you can compose a system from parts. And there's three approaches, and we shouldn't be too quick to assume any one of them over the others. So the first approach is the topological composition, where you imagine a system being composed of different components that are somehow connected to each other. And this is, I think, the most obvious one, at least probably if you're from a computer science or engineering background, you might think about this type of composition. But if you're a physicist, or you might think about more of a spatial composition. So here we just take an object. We don't really break into components. We just break it down into cells or to little elements of different shapes, which fit together. And then each shape has one value or has a uniform a value associated with it. And then the model is composed of all these different cells. And then finally, we've got the functional decomposition. And here we don't really break it down spatially at all. We break down the system into functions. So in a building, you have human behavior, and as being one sort of function. You also have heat flow, but that encompasses the whole system. You could also have sound, for example. So these things don't have clear physical boundaries, but there's still a way of decomposing a system. So okay, now that I've shared that background, now let's dive into the composite node. So a few things to notice. First of all, the composite node is, of course, composed of other nodes. So you can put an atomic node inside one of those nodes in the middle. The other thing to notice is that the outside of the composite node, the interface is exactly the same as the atomic node. If we just switch that here, and let's switch it back. So from the outside, you can't really tell the difference between a composite node and an atomic node. And that means that you can actually put a composite node inside a composite node. So that's how hierarchies are formed. Okay, so let's look further inside. Let's look at the most important part is these simulation components, which are, of course, other nodes, could be atomic or composite, and those are the ones that interact during a simulation. And we've seen this before when I showed you this image. You have a set of nodes, you connect them together, but those connections are done within a composite node, which also could be added to the repository. Now let's think, what type of composition is most suitable for this for this approach? Is a topological composition, a spatial composition, or a functional composition? Now, the answer is that it really depends, but the functional composition it deserves some attention because that's the one that really allows people to collaborate. So if you've got different people, one person specializing in sound, another person specializing in heat flow, another person specializing in human behavior, they can each write their nodes separately and then connect them together. And so the functional composition it would represent that approach that allows people to collaborate. Not only that, but I would actually argue that at the end of the day, if you develop a really complex system simulation, you're eventually going to have a functional composition at the top. So let's take a look at this composition. You might have you might have the top people and temperature and sound being three different models. Now each of them could have a separate composition inside, so that you could have many people in the people model, and that would be sort of like a topological composition. And the temperature model might have a spatial composition inside, and the sound model might have a separate spatial composition. But at the top, you usually end up with a functional composition. So that's I think important to keep in mind. All right, so you got your composite node and simulation components which could be based on a functional composition. Now you also have initialization components, because the first thing you have to do is take your parameters, your flow input ports of the entire composite node, and then translate them into the flow inputs of all the simulation components inside. So that initialization step is important, and it can actually be used in order to create a functional composition from your initial data, which might actually be based on a topological composition. So then you run your simulation, and then on the right hand side, if needed, you have another set of components that can be used to produce a set of flow outputs. So let me just show an animation of that. So here's what this looks like. So you've got a composite node. You start with your initialization process, which is a data flow process. You have a directed acyclic graph, and you execute each function whenever you have the inputs required. Then once that's done, you run the simulation using this SyDEVS approach, and that's more of a message passing approach. And then that's when time actually advances. Now you're at the end of the simulation, and if needed, you've got another data flow graph, which finalizes the composite node. All right, so that's the composite node, and we're just going to quickly cover the last two. The function node we've actually just seen. Remember in the I'll just back up quickly. Remember in the data flow portions of this graph, on the left and the right, you have these nodes that are not really simulation nodes. Those are the function nodes that just have one, and you just have a set of inputs, and you execute it once, and it produces the outputs. So that's quite straightforward. And finally, the collection node, and I've got a whole other separate talk on this. But the idea is that you might want to create many instances of the same node. So for example, you might have a node representing a person, and you might want 100 people. So then you use a collection node to instantiate those 100 people. And the collection node is really there to support agent-based modeling. And that's it. So those are the 4 nodes. I'll take questions in a second, but very quickly, to make use of this, we have the framework called SyDEVS, which again is open source. You can go to the URL there, or you can just Google SyDEVS. That's the easiest way to find it. And on the website, you've got a bunch of documentation. You've got a getting started tutorial. So in a couple hours, if you go through the tutorial, it'll show you how to run these various simulations and how to look inside them. Yeah, all the code's on GitHub. So that's it for sort of the overview of SyDEVS, and more importantly, this common form. I've got now a bunch of research challenges that I could cover, but I might take some questions first. If there are any, Greg, or should I just move on and cover
Let me understand one thing. Right now, okay, so the benefit of a differential equation kind of approaches is that everything is uniform. You have giant arrays of state, and you do use a lot of vector operations. It's very homogeneous. That's actually the weakness of those. But they're very efficient. Here you have a lot of heterogeneous agents running around with a lot of unique operations, which means that it doesn't seem like they fit nearly as nicely onto like vectorized hardware or parallel hardware. What trade-offs have you found in terms of efficiency?
Yeah, that's a good question. I think that's actually one of the research challenges I was going to pose, because the efficiency is I think an outstanding challenge that we haven't looked at so much. I guess the lazy answer is that, since it's at the core, it's C++. So at the end of the day, if you really want to access different hardware, different technologies, you can put that in. And if you find that the composite node and the collection node aren't giving you the structure that you want, you can always put your code in an atomic node, which basically lets you define whatever structure you want, but it doesn't help you do it. You have to do it yourself. So I would say that if you have a complex system simulation and one aspect of it is really computationally demanding, then if necessary, I would just recommend using an atomic node and then doing whatever is necessary inside that node.
That makes sense.
Yeah. Okay. Yeah. We can maybe come back to that, because actually that's a topic. Because I did want to, I know a lot of people are probably interested in data science. Other people are interested in high performance computing. So I wanted to raise these topics in this discussion. So why don't I go on and do this next part? So let's look at some modeling and simulation challenges, and then I'll relate that to this idea of putting everything into a common form. So first, this is a really recent paper where these authors use machine learning to basically learn a physics simulation, and that allowed them to do much more complex scenarios and solve them a lot faster than if they were to solve the equations from scratch. I think you might have seen this paper. I think it got a fair bit of attention. So that gets us thinking. Okay, well, so what does that mean for this approach? Well, remember, with this approach, the idea is that all your simulation models are in a common form. They all accept these different types of inputs and outputs through these types of ports. So could you come up with a general learning solution? Could you figure out a way to take any model and then just basically apply a bunch of inputs to it and observe the outputs and learn it, so that no matter what it was being simulated, a person could then benefit from this machine learning approach and perhaps get results faster with ideally only a small loss in accuracy. So that's the first challenge. It's not something I've looked at, but anyway, can a single AI process learn any simulation model, as opposed to having to apply AI separately on different types of simulations? All right, now let's shift to another perspective. Now, I showed you DEVS earlier, that's from the 1970s. But in the 1990s, an alternative or a new variant came out called parallel DEVS, and the second author, Bernie Ziegler, is actually the same person that invented DEVS, which is now called classic DEVS, the 1970s version. And the idea was, I think, to replace classic DEVS with this parallel version. And the idea is, of course, that Moore's law was going to run out, and so the only way to get things to go faster was to do it in parallel. And so why not make DEVS parallel inherently? So whenever you define a DEVS composition, it will automatically run the nodes in parallel. All the different events will be processed simultaneously for all the nodes. So that was the idea. Though, when we did SyDEVS, we actually used classic DEVS, so parallel DEVS hasn't completely taken over. And I've been a little bit skeptical as to how well this really works in practice. For example, if you think about a topological composition, yeah, that kind of makes sense. If you have a bunch of components, maybe you could process them all in parallel, especially if the complexity level was fairly similar between the components. But for a spatial composition, that doesn't really make too much sense to me, because now you've really got a huge number of elements, and you're probably gonna have a lot of overhead if you try to put them all on a separate processor. So that probably has to still be in an atomic node. But then also let's look at a functional composition, because remember, this is the composition that will probably be at the top of the hierarchy for a complex system. But now you have a balancing issue, because some of these functions, like some aspects, maybe human behavior or thermodynamics, some are going to be a lot more computation intensive than others. So if you simulate them all simultaneously, some of the processes are bound to be waiting for others all the time, and it may not be that parallel. So those were my concerns about parallel DEVS. But I still feel that the underlying goal was a good one, because you don't want everyone to have to really fiddle around with technology to accelerate their code. So I think that challenge is still valid, and maybe you could use another look now that it's 25 years later. Can a single high performance computing solution accelerate any simulation, so that if you put your models in a common form, is there a solution that will technologically accelerate them? Now, one thing that came out of sort of the parallel computing research area were all these notions of time. And so, for example, you've got wall clock time, virtual time, simulated time, vector time, and these when we noticed that these actually words were being adopted, and used in different ways, so that they were sort of used interchangeably. And but it seemed to us that there was sort of a dominant definition for each one. So we came up with this taxonomy here, where we formally define the relationships between different concepts of time. So for example, discrete event time, it formally characterizes virtual time, and virtual time is consistent with simulated time, and simulated time does not contradict vector times. These are formal relationships that we proposed. So that was that's sort of more of a complete work that I wanted to point out. So that if you want to read about that, that's in this paper, A Taxonomy of Event Time Representations. We also spent time looking at simulated time, because if you've got models at vastly different time scales, it turns out that it's not so easy to combine them together, and depending on what time representation you use, you could actually encounter serious problems. So SyDEVS uses a representation, though, that can accommodate any combination of time scales. So if you wanted to have one model in femtoseconds, another one that spans billions of years, I don't know why you'd want to do that, but if you did want to do that, then SyDEVS could handle that. So yeah, again, these are sort of more complete areas. Sorry.
To be clear, you focus on discrete time, not continuous, right?
Can you come again?
You focus on discrete time, correct? Not continuous?
Yes, I guess I would say that the sort of this DEVS approach is a discrete event simulation approach. So you have events at discrete points in time. Though I do feel that if you look at continuous time and you look at integrating equations, you could still do that, because you can still you always have this elapsed time variable, and so you can solve equations sort of for that elapsed period of time. So I found that you're not limited at all in solving continuous problems.
Right, you have to discretize them first, and then you can solve continuous problems, like in differential equations. That's how they do it.
Yeah, and you have to discretize it anyway. So a lot. Actually, but I should mention that is actually a major focus of research. They call it hybrid simulation, where you try to combine a continuous equation-based modeling with this more discrete event approach. So I would caution that with a discrete event approach, you can still solve continuous equations, but there might be a way to make it more convenient, or maybe a bit more approachable, if you have a hybrid approach. So that's something to explore too. And speaking of making things more approachable, that actually gets into the last topic that I want to discuss. And here's a paper that we published in 2015, where we proposed a bunch of visual interfaces for for DEVS, or for this approach that we're doing. This was actually our original goal, even though we didn't quite get it all implemented. And so the idea is, remember I showed you this example earlier of this building being simulated, and all these different nodes working together. So this diagram was drawn in PowerPoint, not SyDEVS. SyDEVS is not graphical, so you have to draw the diagram first, and then when you want to implement it, then you code it, and it looks like this. So on the one hand, you could argue that, so you have to spend an hour or two drawing a diagram, and another hour typing it all in, and what's a few hours for the sake of having a more scalable approach, for having more organized code. I mean, if you're going to be working on this for years, then that's a very small time investment. And while that's true, I think we all know that having an interface that's compelling and graphical and easy to use it is somehow just it helps. It helps things take off, right? It helps attract more users and attract interest. So this is a bit of a liability, even if technically it doesn't. It's only a small investment. So our vision had been to have more of a graphical interface, more of a point-and-click interface where you could draw nodes and connect them together by pointing and clicking. And then when you ran your simulation, you get this nice visual timeline showing when each event was executed and showing the different state variables and values that came out of it, and really having this nice visual experience that would let you rapidly create these compositions and maybe even type code directly into the visual interface. So that was always the vision, and our ideas are published in that paper. We haven't implemented it, but this is something that I think would be valuable to the community. I don't know if anyone on your end might be interested in taking up this kind of thing. But anyway, the challenge is, can we use visual programming to encourage scalable simulation development? All right, so 3 challenges. Can you learn or accelerate simulations using a single AI process or a single high performance computing solution, and can you use visual programming to encourage the adoption of this approach? And of course, all of it is based on this idea of putting simulations in a common form. All right, that's the end of the talk. But anyway, there'll be time for some questions. But I just want to point out that my email is there if you want to get in touch. Our papers are on autodeskresearch.com. And again, you can always just Google SyDEVS to find the SyDEVS framework.
Hi, Rhys. Hi, I'm Stefan. So interesting talk. I'm curious when you think what are the cases where it wouldn't make sense to use methods like this? Like, is there like some level of complexity for your code base or methods when it makes sense to start thinking about like some sort of simulation framework?
Yeah. So that's a good question. So when wouldn't you want to? Well, I guess one barrier is that the framework is C++. So if you're insistent on using a different programming language, that's a barrier right there. If you're doing a really small simulation, you've got a really well-defined scope, and you're confident you're not going to extend it, or you don't want to share it with others and collaborate. Then SyDEVS might add some overhead because you have to set things up a bit. So you have to learn it first of all. So I can see why not just write it sort of as I showed at the beginning with just a simple loop and just get that done. So the initial investments is a bit of a barrier that the hope is that people would overcome that with the idea that you'd eventually be collaborating with the community if you follow this approach. What else? But you mentioned more complex things. Well, the idea of this is to actually support more complex code. Well, like to give an example, I'll give an example that we got a talk a few years ago by the team. I think they did the Anton simulator for molecular dynamics, where they basically implemented biological simulations at the molecular level directly for a supercomputer. Mm-hmm. So there you've got really a single paradigm because they weren't using any multi-scale approaches. It was just basically interactions between atoms essentially. Mm-hmm. And so it was one paradigm, and speed was everything, and everything was close to the hardware. I don't want to say that you couldn't use SyDEVS for that, but mm-hmm. But obviously I think that was more of a dedicated effort. I'm thinking with SyDEVS, I think more about, okay, well, you've got communities that look into this obviously architecture like I showed, but also biological system simulation, geological system simulation, climate modeling. Well, now of course epidemiology is a big one, which depends on human behavior and urban infrastructure like transportation networks. So for things like this, where the real challenge is to get people to collaborate and have different experts model different areas and sort of work collaboratively towards these system simulations that account for feedback loops and interaction between very different phenomena. That's really where the main promise is.
Okay, so like particularly things like you might like different types of models where you're sort of covering different different domains.
Yeah, exactly. Yeah, I call it multi-domain, multi-paradigm, multi-scale, essentially. Yeah, exactly. These very heterogeneous systems.
Are there other paradigms that people that are popular? I mean, obviously, there's lots of different. I mean, probably. I'm not really sure entirely, but I imagine that like many different domains, people have like if you look at like the inside of say like a climate model, for example, they probably. I mean, I don't really know exactly how they organize all their subcomponents, but it's probably I'm sure they have some organizational scheme to let to like maintain to let like dozens of people collaborate on like some of these giant code bases.
Hey, that's exactly right. So for any significant code base, you have to sort of almost end up rewriting SyDEVS from scratch each time. And the idea was to, but of course, because you've evolved it slowly, you had to make certain decisions based on what you've done already. You can't just come with any framework you want. So depending how things have evolved, you might end up with a pretty suboptimal framework, or the one that has to keep being modified over and over as you go on. So climate modeling, that's an area I'm interested in, but I don't have a lot of experience in it. But they do of course decompose the Earth into. They've got the atmospheric model, the ocean model, and the land. The ones I've seen, I think you've got land, basically land, ocean, and atmosphere. So I would personally look at that as different sort of functional aspects. So you have that composition, and then you have a coupler. Often this is done with oftentimes the simulations are written independently, but then you might have 3 simulators. Then you create a separate program that sort of runs all 3 simulators simultaneously. They actually call it co-simulation. I don't know if the client models are done through co-simulation, but if you look at the FMI, that's a co-simulation standard. So that's a popular approach. But I tend to feel that this approach, where you put all the models in a common form, is really the ideal approach. I think that co-simulation will work, especially if you've already written the code. But if you're starting from scratch, I really think that the common form offers the most benefit.
So let me ask you, one real benefit of doing it like the way physics models do it, the mesh is a really important concept. And now what that does, it gives you a lot of efficiency, because you put the things into an array, like in climate models, it's not a regular grid, but something reasonably close to a regular grid, like a hierarchical regular grid or something like that, for performance and parallelism. Your answer earlier was to put things of that nature inside of individual components. But would it be possible to push it the other way around, have a grid of components and get those efficiency benefits?
So you can definitely have a grid of components. So you could have a collection node, for example, which has this is a problem though. I mean, say the collection node had 100,000 grid cells, and each grid cell was an atomic model, and they're all communicating with each other. But that's probably not. I mean, then you're really looking at efficiency issues if you do it that way. But I'd say if you have this very large grid or mesh, and you're trying to solve an equation on it, this is where I kind of differ from other people in this sort of modeling and simulation community, and in the sort of the devs community, because the idea there was to always be able to break models down using these compositions. But I really feel, just pragmatically, if you've got a really large array that you're processing, it's probably not best to decompose that into thousands of separate devs nodes and have this general message passer, exchange data between them. I just feel that would introduce a whole bunch of overhead. I really think you really need to just do one atomic node, and then that atomic node has the whole array, and then you just solve it with whatever method is most efficient. It might be a parallel or distributed method that you implement within the atomic node. even if you do that though, even if you put everything into one atomic node or this whole array, remember that for the climate example, you might have one array for the atmosphere, one for the ocean, one for land, but then you still have to couple those together. So at the top level, the ideal would be to use something like SyDEVS and still use this approach for that functional decomposition at the top. I just feel that as you go down into the hierarchy, there'll come a point where you're just losing too much time by using the composition features of the framework. You're better off making a more specific composition that's more efficient for those smaller, more well-defined problems. Does that make sense?
I think so, except maybe the question I should be asking is about parallelism. How do you run this climate model, 1,000 processors, where a lot of this infrastructure has to be parallelized, maintained, distributed virtual time, while getting the benefits of regular grids that you optimally want to get?
Yeah, so that's the kind of issue where some people in this sort of area would answer, oh, just for each, do a separate node for each processor basically, and then use use this approach to help parallelize it. But I would tend to think that you probably want to put that all in an atomic node, just because that gives you the flexibility to use whatever technological approach is the fastest. Because I just feel that there are certain sub-problems with any complex system, certain sub-problems that really have to be done quickly. And if you can use SyDEVS to parallelize it, or use these compositions to parallelize it, that's great, and I would encourage that. But if not, I wouldn't get hung up about it. I would just put it into atomic node, write custom parallel algorithms, and just basically do the same thing you would normally do even if you weren't using SyDEVS.
Okay, that makes sense.
Yeah.
Yeah, thank you very much. This was fantastic.
Great, thanks. Yeah. Okay.
Yeah, have a great day. Thank you for coming.
Yeah, you too. My pleasure.